of the stern of this ship, the first transatlantic telephone cable was laid in 1955 and 56. It connected by direct telephone line the United States and Canada to the British Isles. Soon after, 2 more cables were laid in the Pacific Ocean. The Alaskan cable in 1956 and the Hawaiian cable in 1957. The success of these cable systems is a tribute to the men from the United States and Great Britain whose skills have made possible the spanning of oceans by telephone lines. Much of the credit belongs to the development engineers who explore and create ways of improving submarine cable telephony. Basically, their job is to develop new coaxial telephone cable systems to operate underwater and connect one shore point to a distant shore point. These systems must be capable of transmitting many telephone conversations at the same time. Amplifiers must be developed to be inserted at regular intervals in the cable. These compensate for the attenuation of the signal as it is transmitted along the cable. To install the cable and repeater system, a cable laying ship is needed. It must be designed to stow thousands of miles of cable in tanks built into its hold. Then, by the use of special cable handling machinery, the ship must be able to pay out the cable and repeaters continuously to their planned location on the ocean bottom. The telephone cable systems now in use were designed to be laid from existing ships. These ships were built for laying telegraph cable, and they did not have any facilities for the continuous handling and laying of rigid repeaters, since telegraph cable systems do not use them in large numbers. Therefore, the telephone repeaters had to be made so that they could be stored and handled like cable. They were made flexible and scarcely thicker than the cable itself. This novel design of the repeaters made the present cable systems possible, but does place a limit on the transmission bandwidth. Future demands for transoceanic communications indicate that there will be a need for broadband cable systems capable of handling 100 or more channels. At Bell Telephone Laboratories, a group of engineers is working to meet this need. The laboratories is the research and development organization of the Bell system. One of its many activities is designing new systems for transmitting information between remote points. Submarine cables are currently one of the major types of systems under development. The coordinating group on submarine cable development consists of electrical and mechanical engineers in the Transmission Systems Development Department. They participate in the overall development of new submarine cable systems and coordinate the skills and resources of many specialists in different fields, both inside and outside the laboratories. One study basic to cable system development is oceanography, which broadly defined includes all aspects of the ocean. The development engineers obtain a great deal of their oceanographic information through a study contract with the Lamont Geological Observatory, which maintains a research ship for collecting data about the topography, sediments, and temperatures of the ocean bottom. This data is collated and interpreted and presented for submarine cable applications in the form of profiles, maps, and tabulations. Engineers from the Systems Development Group, meeting with the oceanographers from Lamont, learn about the features of the ocean floor which may affect cable system design. These engineers discuss this knowledge with other members of the laboratories in a constant give and take of information characteristic of their working environment. As part of the study of the ocean, biologists and corrosion engineers at the laboratories have been studying sections of old telegraph cable recovered during repairs. From these samples, they are able to determine the effect of the ocean and its submarine life on materials which have been lying on the ocean bottom for many years. The biologists have also set up accelerated laboratory tests on materials proposed for future use in cables. They have inserted sections of these materials in a simulated seawater environment under the temperature and microbiological conditions of the ocean bottom. They take resistivity measurements of these samples, which gives them an idea of the relative susceptibility of these materials to deterioration. The structure of the cable itself has undergone considerable evolution. The earliest cable was for telegraph purposes. It was armored on the outside with thick steel wire. The present coaxial telephone cable is also armored on the outside with steel wire. Now development work is directed toward an armorless cable with a strength member in the center and with an outer jacket of polyethylene. This cable is simpler, weighs less, and should be less expensive to manufacture. In order to study thoroughly all aspects of the cable design, experimental manufacturing has been undertaken in cooperation with the Simplex Wire and Cable Company. Under the direction of Bell Laboratories engineers, a complete prototype cable line has been constructed to test possible machinery design and new manufacturing methods for armorless cable. The armorless cable consists of a center strength member of steel wire around which a copper tube is formed. This is the inner conductor. The seam of the copper tube is then welded and the copper rolled tight against the central strand. Over this is extruded a thick coat of clear polyethylene insulation. It is now cooled in a water bath where the polyethylene turns white. The cable next goes through a shaver where it is trimmed to exact dimensions. Now the helical return conductor of the coaxial is applied. It is held firmly by a white mylar tape. The outer jacket of black polyethylene is now applied. A water bath cools and hardens the jacket. The cable is coiled for shipment to Bell Laboratories where it will be tested. One of the tests the engineers apply to the cable is bending. It is bent at various radii to fit a wooden form. A sheet of film is placed back of it and X-ray pictures are taken. The negatives reveal the effect of bending on the internal structure of the cable. This is a measure of the stability of the cable during handling and coiling. Torque tests on the cable are performed at a 100-foot microwave antenna tower. An experimental length of cable is hung from the tower and loaded in tension by an 800-gallon water tank suspended at the lower end. Since there is no rotational restraint, the tendency of the cable to twist may be readily evaluated. Special tanks are used to study the electrical transmission behavior of the cable in a submarine environment. Cable in these tanks can be subjected to ocean bottom temperatures and pressures. The repeaters under study consist of an amplifier inside a rigid protective housing. This larger, more box-like housing is necessary to accommodate broadband multi-channel amplifiers. The electrical connection from the cable to the inside of the housing runs through a vapor seal in the center of the dome-shaped pressure cover of the repeater. This cover seals the housing against pressure and moisture. The interior of the repeater must be at atmospheric pressure and must remain dry during the lifetime of the system. Different types of universal or swivel joints at the point where the cable joins the repeater are also under study. The cover is tested at a pressure of 12,000 pounds per square inch. This provides an ample safety factor for sea pressures at depths up to 3 miles. The weld at the place where the pressure cover joins the housing must be made with a high degree of perfection. Automatic techniques are being developed for this operation. The electron tube amplifier inside the repeater housing must fulfill the needs of the transmission system and still fit into the shape and size demanded by mechanical considerations. To achieve this goal, the circuit engineer and the mechanical engineer must work closely together. The amplifier they are working on is designed to operate unattended for many years. This has been made possible by the development of highly reliable electron tubes. Studies are underway to determine how the virtues of the transistor can be used in future submarine cable amplifier design. Laboratory model amplifiers are being built to check design calculations with actual measurements. Many new materials and component types are being considered for the repeaters. The objective behind all component design is proven integrity, since the reliability of each item must be practically perfect. The scale model plays an important part in development work. This is a model of a shipboard cable tank and stowage facilities for rigid repeaters. It serves as a design tool in planning and constructing a full-scale mock-up. Here the repeaters are stowed on the deck of the ship. Each repeater in turn is put into position for launching. By pulling on the cable end, the cable stored in the tank begins to pay out. Soon the cable reaches the repeater and it starts toward the stern. A full-scale mock-up of a cable tank has been built by the laboratories. With it, the engineers can study methods for stowing and handling rigid repeaters and cable by simulating the actual laying operations. The international flag hoist, signifying that a ship is engaged in cable operations, adds a seagoing atmosphere as the engineers prepare for tests. Methods of coiling cable in the tank and the coiling characteristics of experimental types of armorless cable can be studied exactly in this tank. For future cable-laying ships, it is desirable that the tanks have a capacity of about 2,000 miles of cable in order to lay long, deep-sea portions of new systems without interruption. The full-size repeater is stowed on the simulated deck of the ship. It is carefully moved into position in the trough, ready for launching and overboarding. An engineer at the control station makes a final check. The engine that drives the cable winch is started. The signal is given to commence payout. The winch begins to coil the strand. This pulls the cable around a sheave and out of the tank. When the cable reaches it, the repeater starts off down the chute. Another engineer below is observing the action of the cable in the tank and the behavior of the repeater as it comes down the chute. Runs like this help the engineers to evaluate their design and outline further exploratory work. The full-scale mock-up also permits measurement of the shocks that can be expected within the repeater. Small tape recorders are mounted inside to record vibrations. In the laboratory, these tapes are removed. When the tapes are played back, the shock waves can be studied on an oscilloscope. At the Bergen Research Engineering Corporation, scale models are being used to develop the stowage facilities and cable handling machinery which could be used on board a future cable ship. The quarter-size model includes this circular cable tank and facilities for stowing the repeaters on deck. A Caterpillar cable engine pays out the cable and passes the rigid repeaters without interruption. Translating the drawing board ideas into actual operating machinery allows the engineers to evaluate their designs in realistic terms. The machinery is now ready for a run. Communications are maintained between men at strategic positions along the model. At the tank, the repeater is put into position, and the engineer observing the tanks and repeaters reports that he is ready. The cable engine is started, and the cable is pulled out of the tank. The cable engine must exert a continuous braking action, and at the same time allow the repeaters to pass through without stopping. Finally, the repeater moves over the chute at the simulated stern of the ship and into the sea. As part of the fundamental work on submarine telephone cable systems, mathematicians at the laboratories have updated historical theories and analyzed the dynamic behavior of a submarine cable during laying and recovery. Theoretical calculations have been compared with actual measurements made during the laying of the Hawaiian cable. Finally, all the exploratory and development work on the cable and repeaters is being integrated with the plan and design of a cable ship. To obtain expert guidance on ship matters, the laboratories has a study contract with Gibbs & Cox, naval architects and marine engineers. Together, they are outlining plans and specifications for cable ships equipped to lay and repair broadband cable systems. New submarine telephone cable systems are only one of many types of transmission systems being developed at Bell Telephone Laboratories. They are typical of system developments where many different skills from varied areas of science and technology must be brought together to develop an integrated plan. More fundamentally, these systems are examples of development work which the laboratories performs in all areas that might be expected to provide new knowledge for communications technology.